So welcome to a video for Calculus 1. Today's topic is solving inequalities. You probably learned how to do this in pre-calculus, but in my experience, students maybe have forgotten or maybe they weren't really showed the very best way to do it. So I want to talk about and hopefully get this to where we can use it. And if we can get it well developed, it's something that'll really prove to be useful. So let's start with a simple little equation like this. Y equals 2x plus 5. Hopefully you know that the graph of that equation is a line. So let's graph it. So the y-intercept is 5. We'll make 5 be about right there. And the slope is 2, which means it's going to go up fairly steep. And we'll put arrows to show it goes on and on both directions. So that's not the prettiest graph I've ever seen, but hopefully conveys the information. I want to focus on the x-intercept right there. Of course, the x-intercept, the y value is 0, so you can probably solve it in your head. Subtract 5, divide by 2. So the x-coordinate right here, the intercept is negative 5/2. So what I want you to notice is that if you pick an x value bigger than minus 5/2, here's 1, notice the y-coordinate is positive. And if you pick a value less than minus 5/2, here's 1, down here the y-coordinate is negative. So because the graph is a line, and the line is not horizontal, the slope is not 0. So there is a point, this is true for all lines whose slope is not 0, that all lines that are not either horizontal or vertical, there is a point where the y-coordinates change signs. So we can call that the sign change point for this particular expression, 2x plus 5. Minus 5/2 is the sign change point. And in this particular case, as you move from left to right, they go from negative to positive. So negative, boom, 0, the y-coordinate is 0, and then positive. So I could draw what we're going to learn to call a sign graph of things like this. Not very interesting for one, but it's going to get better. So I'm going to draw a number line here. I'm going to identify the important point, the sign change point, and draw a vertical line here, which kind of breaks the real line into two parts. And we're just going to write a plus here because all the y-coordinates are positive, and we're going to write a minus there. So this guy over here is called the sign change graph. Or maybe let's just call it the sign graph. Got an eraser here somewhere. Sign graph. Okay? Nice and easy for a line. All right. So let me clean this off and we'll go to a new page. Let's do one more example just for the fun of it. Not complicated. Probably so easy it's boring you. This time we're going to take y equals, I don't know, minus x plus 7. Again, it's a line. How do we know it's a line? It's a first degree polynomial. X, the variable, shows up to the first power. It has a coefficient, in this case, of minus 1. And then we have the 7 added on. First degree polynomial, all the graphs are lines. And if we want to find the x-intercept, which is going to turn out to be our sign change point. We're just going to set that equal to 0. And easily, you can solve it in your head. X equals 7. So if I graph the line, the x-intercept is 7, but now the slope is -1, so it's going downhill. And this guy would be, we already calculated it, 7. So the sine graph it goes like this. We got our number line down here. We have a sign change point at 7. Notice this time we have positive to the left, negative to the right. So the signs go from plus to minus. And there's the sign change graph. And every line will have a sign change graph basically like one of these. There will be sign change point, which means it does change signs. It will either go from positive to negative or negative to positive. And we could even be more systematic. This one goes from positive to negative because the slope is negative. Okay? So that easy. Now let's make it more interesting. So what I want to do is solve this inequality. So let's take x plus 2 times 3x minus 5. And I want that expression to be negative. That's all I care about, where it's negative. So I look at these individual factors. They're lines. They're first-degree polynomials. So I know that each one of them has exactly one sign change point. This one changes sign at -2. This one changes sign at 5/3. Okay, and now these guys are multiplied together. Well, we know that when you multiply two numbers together, if they are if they have the same sign, either both positive or both negative, the product is positive. A negative times a negative is a positive. But if the signs are opposite, then the product will be negative. So to solve an inequality where we're interested in negative less than 0, we just need to find out where the signs are opposite. Now, we could make this a complicated algebra problem, but we don't need to, because remember, each of these lines, it has exactly one. This one right here changes sign at -2 and never ever changes again. Because the slope is positive, it's going to change left to right from negative to positive. So I'm going to draw a sign graph of the whole expression. There are two sign change points. One of them is at -2, and the other is at 5/3. Okay. It's really important that I get the numbers here, the -2 and the 5/3, in increasing order. The smallest one on the left, the big one on the right. Okay, now if we pick an x value over here less than -2, notice both of these factors are going to be negative. Okay, this one doesn't get positive until -2. This one doesn't get positive until 5/3. So both are negative. When I multiply two negatives, I get a plus. So we're going to get a plus in that region right there. When I slip over into the next region, then x plus 2 has changed signs. It was negative, now it's positive. 3x plus 5 is still negative. We haven't passed its. So now in here I have a negative times a positive. So the product will be negative. When I move over into this region, now both of them are positive. The product is positive. And then I look back for really the first time and say, now what did I want? Well, I want less than 0. So we're going to take the region right here in the middle. That was supposed to be a star. Didn't work out very well. So here's our answer. Every number between -2 and 5/3. Okay, this is interval notation. And what it means is, just like I said, we get a solution as long as we pick a number that's strictly bigger than 2, but less than 5/3. And of course, there are an infinite number of numbers in that interval. And we've solved the problem. All right, so a few little wrinkles here. Let's go to a new one. So let's take this problem. Solve. Okay, we'll do it in red. 3 minus x, 2x plus 5. And this time I want it to be bigger than or equal to 0. So we look closely. First degree polynomial. First degree polynomial. Therefore, individually, the graphs are lines, which means they change sign at exactly one point. Where does 3 minus x change sign? I can hear you thinking it. 3. Here's our sign change graph, or sign graph. Oops, I've been careless. Let's get rid of that 3. Okay, I can do it. So we have our sign change points are 3 and negative 5 halves. So minus 5 halves is the smaller one, and 3 is the big one. So my sign graph breaks the real line into these 3 regions: small guy on the left, big guy on the right. Now, on the last problem, I kind of talked through a way to figure out the sign in each of these regions. But if we have lines, different lines here, what's important to know is that they change sign at exactly one point, which means whatever the signs are over here, when I move into this region, exactly one of them will change signs. And if exactly one changes, the sign of the product is going to change. So get rid of that. So whatever the sign, whatever we decide the sign is over here, I think on the last problem it was positive. Whatever we decided is here, it's going to be different here, and then it's going to be different there. So really, all I need to do is figure out the sign in one region. And when we can do it, and we can do it here, we love the number 0, that if I plug 0 into this expression, I get 3 times 5. That's a positive number. Therefore, this expression will be positive for every number between minus 5 halves and 3 because we have not crossed a sign change point. However, when we do, the signs are going to alternate. When I move, get rid of that arrowhead and put it over here. When I move into this region, this guy, 2x plus 5, is going to change signs. 3 minus x is the same, so the sign of the product will change. And when I move over here, 3 minus x is going to change from negative to positive. Sorry, positive to negative, which makes the product change signs as well. Now, for the very first time, really, I look and say, well, what is I wanted here? I actually find the sign everywhere, but I only really want to know where it's positive. So once again, it's the region in the middle. So we're going to take minus 5 halves to 3. And there's one more little wrinkle here. This one, unlike the last problem, we say, well, we want it to be greater than or equal to 0. Well, where is this going to be equal to 0? It's at exactly the sign change points. Okay, because 0 times any number is 0. And so when we want to include those, that is, we want to include, we use square brackets. I'll turn these parentheses into square one, and we do it down there. So there's our answer. And if you want to write it in algebraic form, it would be minus 2 halves less than or equal to x, less than or equal to 3. So we can write it this way, or we can write it that way. It doesn't matter. We have a good answer. Okay? Let's try a new problem. If I can get rid of this one. All right. Let's try this one. I guess we'll still do it in red. X plus 2 over 7 minus 4x, strictly positive. Got a stray mark in there. Let me get rid of it. Oop. Now I got rid of the fraction line. There we go. So this is not a product. This is a quotient. But you can think of a quotient. Quotients are actually a lot like products. Let's think of this: x plus 2 times the number 1 over 7 minus 4x. And you can see the sign of this guy is going to be the sign of the denominator. If the denominator is positive, 1 divided by it is positive. If the denominator is negative, 1 divided by it is negative. So even though this is a quotient and not a product, it's not going to change the way we solve it. I still need to analyze the signs individually. So here goes our sign graph. We have a sign change at -2 and 7/4. -2 is the small one. We'll put him on the left. 7/4 on the right. We plug in 0, happens to be in the middle again, and I get 2 divided by 7. That is a positive number. The signs will alternate. And now, for the first time, I say, well, what exactly did we want here? We want greater than 0. So once again, we pick the region in the middle. Get away. Or less than x, less than 7/4. Either way we want to write it. Now, I've been a little bit careless in that the middle region has been the solution to all of these. And I think maybe on all of them, 0's been in the middle. Let's do one that's totally different. Go away. All right, so solve. Let's take something like x squared plus 9x, and we want it to be bigger than or equal to 0. Okay, so maybe this is not a fair problem. X squared plus 9x is not a line. Maybe you'll recognize the graph of that as a parabola. But we can factor it into linear, so that's what we're going to do. Take the x out, I get x times x plus 9. So now we have first degree polynomial, first degree polynomial. Now it's exactly like the problems we did before. X changes sign at 0, x plus 9 at -9. -9 is the small guy. Now I can't plug in 0 to get the sign because 0 makes it equal to 0. But I can plug in a number like 1, and you can see we're going to get a positive number, and then the signs are going to alternate. We know they are because these are lines. They're not complicated. We can count on it. Now, for the very first time, I say, well, what is it we wanted here? Oh, yeah, bigger than or equal, positive. So I'm going to take the region. Here's our answer. Every number below -9, we write it like this in interval notation. Notice we're including 0. When you plug in -9, we get 0, so we'll include that. Then maybe we could use a union symbol. You probably have seen that before. And then we're going to start at 0 and go forever. So there's our answer. I'm not going to write this one in algebraic form. We'll just leave it like that. Beautiful. All right. Let's solve a very similar but slightly different problem. Okay, here we go. Now we'll go back to black. So x over x plus 9. Strictly bigger than 0. Okay, so just like before, this is a quotient. That doesn't bother us. We know the signs of x and x plus 9 control what's going on here. I want to make this bigger than or equal to 0. There we go. So I have a sign change value at -9, the denominator. and at 0 again. Notice those are the same sign change points as the last problem. The only difference is we're throwing this guy down in the denominator. Because the expressions, the linear first degree polynomials are the same, the signs are going to go the same way. Plus, minus, plus. And then we say, well, bigger than or equal, we want to include all the endpoints, except when x equals 0, no problem. 0 divided by 9 is 0, and 0 is bigger than or equal to 0. So 0 is part of the solution, but negative 9 isn't. We cannot divide by 0. If you plug negative 9 into that, you get negative 9 divided by 0, and that doesn't make any sense. We'll learn to say later D and E does not exist. Meaningless. So even though we're saying bigger than or equal, we can't include the 9. So our answer is going to be every number less than negative 9, but not negative 9, so use a parenthesis. And then we'll start at 0 and include it, and we'll go forever. And that's our answer. Okay? One more problem. I've kind of shown you all the weird little things that can happen. We'll do one more, and just to show how powerful this is. So, solve. X times 2x minus 3 times 5 minus x times 4 plus 9x times x plus 2. We want that to be strictly positive. Okay, what a mess. How in the world can we solve it? Well, once again, look carefully. All these factors are first degree polynomials. They all will change sign at exactly 1 point. On either side of that point, they never ever change sign, the individual factors. So all we have to do is find the sign change point. I'll write them down below. 0, 3/2, 5, negative 4/9, and negative 2. So we need a big long number line here. The smallest number there is negative 2. And then negative 4/9, and then 0, and then 3/2, and finally 5. So, increasing order. Notice I don't really care about drawing at the scale. I don't care how much space is inside here. It doesn't matter. The only thing that matters is that I have sign change points, and they're in increasing order. Now, I need to get the sign in one of these regions. Here, here, here. And, I can't plug in 0 because it's a sign change point. But let's plug in the number 1, and we'll keep track here. I'll write it above here. Do we get a positive or a negative? If I plug in 1, I get positive, negative, positive, positive, positive. Right? You get the numbers don't matter. We get 3, 13, 4, negative 1. And 1. Now, if I multiply, this is a plus sign, 4 positive numbers times a negative, I get a negative number. And where is 1 on the number line? Well, it's bigger than 0, but less than 3/2. So this region, the expression is negative, and because they're all first degree polynomials, it's just going to change, alternate. Now, what are we interested in? Positive. Here's our answer. Everything less than minus 2. Plus, everything between, I can't read my writing, minus, this is a 9, minus 4/9 and 0, plus everything between 3/2 and 5. Easy as pie. All right. I'll make some problems available for you to solve a little bit later. Another video, or maybe I'll something in class. We'll see. That's it for now. Bye.